everyone. To the organizers, thank you for the wonderful invitation to be here. My apologies that I arrived 5 minutes before starting. I live in Boston and traffic is variable. So normally I was here last week and it consistently takes 30 minutes and today it took 50. So here I am just in the nick of time. But as Mike said, I made it. So anyways, so the title of my talk is Sparsity and Symbols in Kolmogorov-Arnold networks. And sparsity is an important area in machine learning. This is something that Mike has thought about a little bit in the context of Kolmogorov-Arnold. We want to make big networks smaller and understand theoretically tractable ways to make progress on that because we want smaller neural networks that are still performant. Symbols is a nod to symbolic regression, which is one type of thing that physicists do. We do many things beyond that. Maybe I should confess at the beginning, I'm a physicist. And I will prove that I'm a physicist at one point in the talk by having an absurd number of indices in some of my equations. So my apologies for that. Symbolic regression is where you take data and you try to have some very simple interpretable equation that fits the data well, so that you might call it a law of physics if it generalizes to sufficiently diverse data in physical settings. To be contrasted with a neural network, which is some very big equation. It's still an equation. We regress on this, but it's not the most interpretable thing in the world. So symbolic regression looks a little more like normal equations. So my outline, let me actually push, perfect, that'll be fine. My outline, this is a nice tall board, is first I want to review a little bit of Kolmogorov-Arnold. These are what we call cans in our work. And then the second thing that I want to ask is about sparsity. So namely, one of the questions that sometimes comes up with cans is, isn't this secretly just some sort of sparsified MLP? And that's the thing that I want to put teeth on. If you're not familiar, I'm going to say MLP a lot. This is just a standard feed-forward deep neural network. It is the thing that you first learn where you take a bunch of affine transformations and compose them and act with nonlinearities and then iterate over that. That's called a multi-layer perceptron, an MLP. So the sparsity perspective that I'm going to take is MLP to can. It looks like Mike has a talk later in the week, Mike Mulligan, from a similar perspective, but it looks complementary as far as I can tell, which is great. So we're going to be engineering cans within MLPs rather than learning them. And then given the engineered can relative to the MLP, at the end, I will pull up slides and show some experiments, but I thought in this setting, it's better to start with chalk. And finally, I'll go to something more applied, which is to talk about symbols. Namely, can you have some sort of vision-based large language model that then you pipe into a can and then you do symbolic regression with this? So this is the outline. I will try to keep this here so that we can orient to where we are. But let me begin a little bit first with the can section. So to remind you, there is a theorem, or I should say a set of theorems. I will comment on that later. There's quite a history of this due to Kolmogorov and Arnold. That says, given a multivariate continuous function, on a box, in a multivariate continuous function on a box, there exists a representation of this form. There's a way to represent it, such as this. F of x1 through xn is some sum from q equals 0 to 2n, capital phi q, sum from p equals 1 to n, phi pq, xp. So that's perfect. With phi pq, a univariate function, and similarly for this phi capital Q. And there was a really nice, I learned about it from Mike's paper, actually. It was an AMS bulletin or something like that from maybe 5 or 10 years ago, recalling some of the history of this in the context of Hilbert's 13th problem. And it goes through the proof a little bit, and it sort of goes through the history. There's different versions of this theorem. I'll mention at some point there was a paper from last year that sort of categorized a lot of them in the context of machine learning. But the basic idea here is that to ask the question, are all multivariate functions sort of secretly univariate functions composed out of appropriately nonlinear univariate functions together with addition, together with further composition? And the answer that the theorem provides to this qualitative question is yes, that all multivariate functions can be decomposed in this way. In the language, these are sometimes called the inner functions. These are called the outer functions. And this is the subject of much discussion in the machine learning literature going back quite some time. The caveat is that the inner functions are not necessarily smooth. Okay. And there are various pathological cases that people have studied. Yes.
Just a tiny thing. The outer sum should go to 2n plus 1.
2n plus 1, thank you.
By smooth being continuous, or to me, you're not even assuming that f is smooth.
I'm not necessarily assuming that f is smooth, but even if f is smooth, there are pathological cases where the inner functions can be very sort of strange things. And so part of the history of this literature is that I mean, it goes back to the 50s and 60s. There's I mentioned the AMS bulletin because Kolmogorov and Arnold sort of had a back and forth in the literature, sort of how much can you beat down the assumptions and so on and so forth. But even since then, there are, I wouldn't necessarily say improvement. There are different versions of this theorem that weaken the assumptions, and one of them was the one that Mike used in his paper. Yeah, so these inner functions can be strange. And we'll talk not too much about that today. There's different versions of the theorem, different assumptions. The spirit of what we're going to do in this talk is sort of the spirit of what we do in machine learning, which is to sort of take it's also what physicists do, take some inspiration from the mathematics literature and run with it and see where it goes to.
Question.
Yeah.
Inner functions are they Lipschitz?
Yes.
But they can't be made C1.
Yes, exactly. Good. Okay. Good. So a couple of notes on this. Okay, so there exist many versions. And even the original KA story was a back and forth between K and A, student and advisor. There's this machine learning article that I like from last December that I'll refer you to because it lists a whole bunch of different versions of the theorem and discusses them and also goes quite a bit into the history. So the history of this is pretty interesting, but it's not what we're going to focus on today. So there do exist stories that I'm not going to go into about smooth approximations. And part of the reason that I mention this is that normally what we talk about in machine learning is approximation theorems. There's this famous old result due to Sybenko from the late 80s that says if you take a standard neural network and make it wide enough, there's like this width parameter. If you make it wide enough, you can basically approximate any function and the error is going to get smaller and smaller as the width gets big. So that's normally what we talk about is approximation theorems in machine learning. This is a representation theorem saying that there is a representation that exactly represents the function given the assumptions. But one of the things that we're going to do anytime we're either putting it on a computer and we have truncation error associated with being with floating points, or alternatively, if we're fitting a neural network to it and we're not letting, there might be some approximation error in these inner functions themselves. There's also some literature not about KA representation theorems, but about related approximation theorems. So there do exist smooth approximations under certain assumptions. And finally, this is sort of the most important note that I'm going to make here. So when you look at this equation, if you've ever seen the equation for a neural network, well, this looks like some sort of equation for a neural network. For me, a neural network is just a function with parameters in it, right? It's a family of functions. Normally, we don't, for my class the other day, I did call a linear function mx plus b a neural network just to make the point that linear regression and training it is not so different from the loop that we use to train neural networks. But normally neural networks are some sort of complicated function with parameters in it where you regress on the parameters to achieve some goal. But you could imagine for these inner and outer functions, if you represented these in some sort of basis or as some sort of neural network themselves, they're going to have parameters, and solving the regression problem is what's going to let you take a step towards the target function you're trying to represent. So this looks like a neural network, but there's a key difference. And the key difference, so the fact that I have my function taking values in R is why I only have, why I don't have an index on the output here. So let's not pay attention to this. Let's pay attention to this. This inner function depends on XP, and it sort of maps us to the qth coordinate in some auxiliary space before you act with the rest of the compositions. And so what this looks like is what's called an activation function in machine learning, but the activation is on the edge. So normally, we draw pictures of a feed-forward neural network, and we have nodes in this graphical representation. And the affine transformation takes you into these nodes, and then you act with a nonlinearity on the pre-activation and get something called the post-activation. But in particular, you have an activation per node, and by convention in standard deep learning, we normally take a fixed activation for all of the nodes. Whereas this is something that does not depend on one node. If you're going to think of this as living on an input node, and what's coming out is living on an intermediate layer node Q, then phi PQ, the activation function, depends on both the input and output. So graphically speaking, you can think of it as living on an edge. Yes?
Yeah, there are some variations on neural networks that you can motivate by talking about behaving nicely under some symmetry or some operations on the inputs.
Yes.
So here one observes, for example, that diffeomorphism on one of the variables would behave nicely in this framework. Is there some characterization of the K in those terms?
In terms of symmetries, yeah, I've not thought much about the symmetry in the KAN context. There might be literature on equivariant KANs, but I'm actually not familiar with it. Yeah, thank you. Okay. Okay, and so these are, this is the basic statement that this looks like a neural network where the activation is on the edge. And so part of the perspective of our work last year was to say, okay, this is the formal theorem. It sort of has depth 1 in the sense that you're doing a relatively simple composition here. You're not going super deep. And it has a width that is sort of the minimal thing, as I understand it, that's needed to make the theorem hold. But what if you just sort of like blow the doors off of this and let yourself have lots of width and lots of depth? And if you define a neural network of that type, does it perform well? So, so this is the definition of a Kolmogorov-Arnold network. A depth L function R to the N0 to R to the NL. Kolmogorov-Arnold network. It's like this. And so I'm going to have, maybe I'll try to work backwards. I'm going to take some input xi0 for the 0th layer, and I'm going to act on it with some inner function. Okay. And I'm going to sum that up. But you could imagine yourself repeating such a process till you sort of get towards the outer layers. This is not the part where the indices get bad. This is relatively simple indices relative to where I'm going. Okay. And of course, there's all sorts of opportunities for index error here, which I'm mostly not going to worry about. Okay. So here's my function. And it's very much in the spirit of the theorem. One thing to say here is that where, I'll talk about the function in a second, where the phi k activations, if you think graphically about this function, they're activations on the edges. And something to note is that in our context, we're imagining that these phis themselves, we parameterize. And so these phis have parameters of some type, and they're learned. So we take the functional form that sort of in spirit is motivated by this representation theorem. We have the activations on the edges. We have the inputs coming in, get it acting on. Of course, it's univariate plus addition is the spirit of the Ka theorem, that univariate plus addition plus composition is all you need for multivariate functions. And we let ourselves take some width, n0 and all the way up through nl minus 1. That is some definition, some parameters that help define the network. Then we also let ourselves take some depth. So we're taking something very much in the spirit of the equation in the theorem, but we are allowing ourselves to generalize in width and in depth. And we're also letting these phis be parameterized so that these activations can be learned. Because one of the things that's very different from this formula about relative to a standard feed-forward network where you often take fixed activations is that these, in principle, might be very, very different functions from one another. And so unless you're very smart and can cleverly pick them ahead of time, you want to learn those activations. So that's what we will do. Good. Perfect. I have a couple of more comments from our paper. Love the tall board as a tall person, take use of it. First of all, there's many applications, okay? So people are using this in all sorts of different contexts. In our original paper, we did that too. My gateway into this was via knot theory. We wanted to do cans for some problems in knot theory and some interpretability. There was a beautiful DeepMind Nature paper in 2021 that did a similar sort of thing with MLPs, and we wanted to reproduce and in a certain sense improve upon their results using cans. Perfect. There exists an implementation. So part of the thing that I think made this fun for people when our paper came out is that Ziming Liu, who is the lead author, was a PhD student at MIT, wrote a fantastic implementation, complete with graphics, and the graphics will actually play a role in the later part of the talk. But there's an implementation that's very good called PyCan. It is written by a physicist, not by an ML engineer, so it definitely could be faster. But for the basic bells and whistles of playing with this idea, he did a really fantastic job. And the final thing that I want to talk about is there was a story about B-splines. So B-splines are certain piecewise polynomial functions that are used a lot in 1D approximation theory. And the basic idea was to let our activation functions that we're learning be this B of X I won't worry too much about, but to be some sum over some B-splines with coefficients I. And these are the things in our paper that are learned. But the nice thing about using B-splines is that there's an extensive 1D approximation theory about them. Before we get to that, something I should say is that these things have a notion of locality. So there's something in the machine learning called catastrophic forgetting, which is the following idea. So catastrophic forgetting, if you take some amount of, if you train your neural network on some amount of data that lives over here, and you start to develop good approximations over here, some neural networks have an implicit non-locality that when you then take this trained network that was trained down here and train over here, it screws up what happens in the original region. It's called catastrophic forgetting. There's a lot of evidence on this and a lot of literature on that. The locality helps with that. The main point that I want to make is a scaling result under this B-spline assumption. So if n is the number of parameters of your neural network, and L is the test root mean square error loss, and D is the data dimension, then the question that you want to ask is something like, how does the loss scale with the number of parameters as a function of the dimension? So there's this scaling exponent alpha that in principle, in general, should depend on the dimension. And for this B-spline can, the result is that this exponent is k+1, where you use a degree k B-spline. And we took the case of cubic B-splines, so they're degree 3 piecewise polynomials. And this got us this n to the -4 scaling exponent if you plug in k = 3. To be contrasted to other results in the literature. So for example, I think it's for Relu, but it's more general. This is the result of Kaplan and Sharma from 4 or 5 years ago. There's this D dependence in the scaling dimension. And so this was one of the things that we were excited about under certain assumptions about using the B-splines, which is related to whether or not you have a smooth Kolmogorov-Arnold representation. This B-spline can gets us n to the -4 when k is 3, independent of the dimension. And so in some very simple examples, that does not guarantee that you're able to find said function. So under some very certain, in some very certain examples, we were able to actually show this n to the -4 scaling and to show that it was actually persisting as we increase the dimension. Yes?
So how should we think, like maybe in practice, be thinking about the relative sizes of D, K, and N, these various parameters?
Yes. So in the simple cases that we took to show that we were getting this 1/n to the 4th independent of dimension, we took like D = 1, 2, 3, 4. Of course, in high dimensional data in machine learning, if you wanted to go very far, you might be looking at, thousands or hundreds of thousands for the data dimension. The spaces can be rather big, especially image data if you have lots of pixels and you have different channels for R, G, and B. So that's about D. So we were showing this in low D, but in principle, it goes to higher D if you can optimize and find it. You also asked about N. In some of ours, we were doing hundreds or thousands of parameters, but performant large language models are upwards of 1 trillion, probably even over now. So there's, yeah, I mean, you can download open source large language models with 100 billion parameters and run them on a powerful laptop.
Sorry, what was K again?
K here is the degree of the spline. Is the degree of the spline.
And what would happen if you took a different basis, like Chebyshev or Fourier?
Right. So when I say that there's, I shouldn't say there's just many applications. A lot of people just iterated on our ideas and take a different basis. I don't know the question there, but I know the question. I don't know the answer. The question that you would want to ask is how does the detail of Chebyshev 1D approximation theory work, and how does that propagate through into a similar theorem, if it does? In principle, the basic idea is that you want to take something that's really good at doing 1D approximations and then use the can to get you to higher dimensions. I don't know the answer in the Chebyshev case, but there are Chebyshev follow-ups for what it's worth. Okay. Cool. This is all I wanted to say in the first part of the talk. To give you a basic sense, there is a representation theorem, many versions of the theorem. There are different smooth approximations, but our perspective was just do what we do in machine learning. Don't worry so much about the details. Take this as inspiration and try to write down a neural network. Any questions other than this? So I'm going to erase all of this to start the sparsity section because I'm going to need some room. My timing's good enough for what I was hoping. So those are the main results from the original paper, at least as I see them. This is what I'm about to tell you now is work in progress with Thomas Harvey and Fabian Rula. Sparsity. I mean, again, just general. So when we talk about sparsity in neural networks, we mean a lot of things. We mean how to, I mean, roughly, we mean how to take a big neural network and make it smaller in a way that, you know, still makes it performant enough. Because we want smaller neural networks that are great, because we don't want it to always be the case that, you know, cutting edge stuff has to be at 5 companies with billions of dollars. So people talk about that in the context of what's called democratizing AI so that more people can do cutting edge stuff. And so understanding theoretically and empirically how to sparsify neural networks is a good idea. So the basic setup that I want to claim here is that a can is equal to a sparse MLP. Where there's some sparsity map I'll tell you about. And this has a guarantee. And what I mean by that is that we worked on cans because there was a theorem to sort of motivate it and because they were interesting in doing well. A lot of sparsity work in the literature, they look for various sparsity patterns that are going to be good, but there's it's not often the case that there is a sparsity map that has a guarantee. But what I mean by the guarantee is that the MLP has a guarantee in the context of the universal approximation theorem that MLPs are really good at approximating. Then when we apply our sparsity map, another sort of guarantee, if you'd like, takes hold, which is the Kolmogorov-Arnold theorem. So this is a sparsity map with principles. And the key thing, if you want to, the key thing, I'm giving you a sketch. If you want to turn an MLP into a can, you somehow have to take fixed-ish activations on the nodes, and the sparsity map has to turn them into learned activations on the edges. Okay, so that's the key idea. Okay. And so this is going to be a few step process. There are 2 places in the talk where the word geometry will appear, and I'll be very loose with it. A lot of the work we do in physics is much more tightly tied with geometry than this, but I'll give you one place. So, so I'm going to start with what I'll call MLP big. And the nice thing about MLP big is it looks like the thing you know and love. I'm going to take it to be width. And I'm going to try to do both equations and pictures with bn squared with varying activation in some set, sigma 1 through sigma b. And so the basic picture here is that you have some sigma 1, some sigma 2, sigma 1, sigma 2. So there are these pieces that are repeating. And this will be a post-activation coming out of the ELF layer here. And so I'm gonna, this crud just means dense. So I'm gonna have dense connections to the next layer, which means that I just have a matrix taking me from one layer to the next, a matrix of parameters that doesn't have any special properties. It's completely filled out, so it's dense. Alternatively, the graph is complete. All right, sigma 1, sigma 2, sigma 1, sigma 2. I'm just emphasizing in my picture that the activations are varying. Good. And here's my, very dense friend again. And the equation for this, so good. So when things come in, they're off into the node, they're often called pre-activations, and then they get acted on with the activation. And when they come out, they're called post-activations. I'm going to use H for post-activations and Z for pre-activations. And the superscript is just, I'm imagining this is some chunk in some arbitrary MLP. So there's stuff coming in here and there's stuff coming out there. And I'm just zooming in on this chunk of this MLP with a couple of layers, fully dense connections, varying activation, and width B capital N squared. And so the equation here for the L plus 2th layer pre-activation, I'm going to write to follow a convention semicolon alpha to remind ourselves that when we're doing this, that we're at some intermediate layer of a neural network, but it actually is acting on some data input. And so you're actually training on some data, of course, with some large batch, and there's some data index alpha. So I'm going to track that around just to remind ourselves that this depends on data, even if we're not being explicit about it in terms of what the data is. Okay.
Jim, why did the indices repeat in the vertical columns, like sigma 1 twice?
So sigma 1, sigma 2, and I'm going to imagine that I have these blocks appearing multiple times. The dimension of this is bn squared. I'm going to have these blocks of sigma 1 through sigma b appearing multiple times. And it's actually going to be important because those are going to become the basis functions for the CAN activations.
I see n. Is the n your previous capital N?
This n is actually, you're going to see it emerge in a second when I do the next step. For now, just take it to be a natural number.
The different segments are different activation.
You can, yeah, I guess it would be, there are different activation functions because otherwise you might collapse it down and call it something smaller. But in principle, you could choose them all to be the same, which would be equivalent to taking b equals 1. Yeah. Okay, so this is WC, sum BC, L, HC alpha of L. Okay, so this is just the standard equation. I turned the biases off if you're familiar with biases, just for simplicity. And so I have the weights acting on the post activation, totally standard. I then have the activations acting on this pre-activation here, but I'm doing it in a way where I let myself have a bunch of different activation functions. And then I have another matrix acting that is this. So WL is here. This is this map. And WL plus 1 is this map. Okay, so here the matrices are in the space of real matrices of size bn squared, And I have run out of room to sort of go south here, I think. So I'm going to go to the next board. I'm going to go high. So the idea is to map this picture up to what I'll call MLP small. But to do this, I'm first going to take W to be of the form this is apologies for the abusive notation. This B here is something that is setting the number of activations. This B here is a matrix factorization of W. Okay, is one of the factors in a matrix factorization of W. And in particular, I'm going to take this to live on the determinantal variety of rank n matrices in this big space. So I have this general W matrix which lives here, but then you can say I'm gonna choose a lower rank friend here where this is n by n. Sorry, this is bn squared by n, and this is n by bn squared. So this is living on the determinantal variety in this matrix space. It's real. Of course, there's a lot of algebraic geometry literature on determinantal varieties. We have not been diving into it too much yet. We will soon, partially because we've been prioritizing the experiments, which I'll get to. Okay, so when you do this, the picture changes a bit, and I'm going to have to sketch a little. So this is my original thing that I had. I guess I can use some colored chalk to help make the point. So this is the original thing that I had. And what I'm going to do is take some blue nodes in here, where now, by this factorization, I have some intermediate layers where there's some sort of bottleneck. This has size bn squared, this has size n, this has size bn squared, this has size n, this has size bn squared. Okay, and so B is this map that takes me down to here, A takes me back up. It's just, and these are all dense still. I'm sorry, I should draw them in a way that looks sufficiently complicated. These are still dense. Very good. And so now, if you'd like, if this was ZL plus 1, ZL plus 2, by taking the matrices to live on this subspace, I've sort of grown intermediate layers, if you would like. And in that growing of the intermediate layers, I need another name for those pre-activations. So I'll call these ZL hat. So this, if this is ZL, then the matrix down to the bottleneck layer, I'll call ZL hat. The hatted friends are this other layer. So then this is ZL hat plus 1. Okay. And of course, there are equations for this. This is going to work, I think. So now, good, I should draw a picture. So this whole thing is what I'm calling MLP big, this intermediate layer here. This chunk here with these new layers is what I want to call MLP small. And of course, if you'd like, MLP small is sitting within MLP big. If you had a truly deep neural network of width n and this just kept going, you would like zoom in on any little subchunk and you could turn each into an MLP small by passing to the determinantal, right? And so in particular, these you could give in MLP big with L layers, it would turn it into MLP small, sort of stacked more and more and more. It's a perfectly fine thing to do. And the equation for this is Zi alpha L plus 1 hat, which is sum on B equals 1 to Bn squared, BIB L plus 1, sigma B mod B, sum J equals 1 to N, A B J L, Z J alpha L hat. And so this is this equation for this MLP small here. I have these intermediate layer, this new layer that gets that we get by passing to the determinantal. Notice that now in this perspective, I have alternating like non-trivial varying activations with some big width, and then at the next layer, I have identity activation on small width, and there's this alternation. Perfect. And something that I did here implicitly is I am trying to separate middle Latin indices from beginning of Latin indices. So these big layers are going to get early Latin. And these intermediate ones here are going to get middle Latin. Okay. Good. And the key fact is that my early Latin indices, which go from 1 to Bn squared, I'm going to do some sort of factorization of this into KQL, where K and L are from 1 to N, and Q is from 1 to B. And so this is, so there's some choices I made along the way for the sake of pedagogy, but if we're going to map activations from nodes to edges, I need some way to have the n nodes here and the n nodes here have n squared edges between them, but I have these big intermediate layers. So it's not sufficient to be there yet. I need to do something else, but these dimensions are chosen intentionally so that I can do an appropriate sparsification here. Maybe I'll just do it and I'll take questions. Maybe I'll just leave, I'll erase this for now because I'm going to say the same thing up top. So finally, this is what we call MLP small. I'm going to get to the N limit, single layer Kolmogorov-Arnold layer. And the basic idea is to reshape the B index to LQK, where this has Bn squared parameters. This has, sorry, this runs from 1 to Bn squared. This one runs from 1 to N. This one's from 1 to B, and this runs from 1 to N. And in doing this, this equation becomes equal to sum LQK, B I LQK, K plus 1, L plus 1 rather, sigma Q, sum from J equals 1 to N, ALQK. Told you I promised I'd show you I was a physicist. Yeah. LQK, ZJ alpha. So all I'm doing here is I'm taking this index with the bn squared things and I'm factorizing it into n by n. Okay. And then the last thing that I want to do is I want to sparsify by inserting delta IL and delta KJ. And so this is basically saying that I want to have one edge connecting the ith node with the jth node here, the ith node with the elf node, I guess, in this notation.
KJ,
Pardon me?
KJ or KH?
Let me see. I'm sorry, KJ. Yes, thank you. KJ. Yes. And so when you do this, what you get is that this sum collapses onto some QK, sigma Q, A, I, Q, K, K, Z, K, alpha, L hat. A lot of indices, and I will define this. Now looking at this way of doing it, I, Q, K, K, Z, K. Notice now only one variable is coming in here. It is the kth variable here. There's no extra sum in here, so this now is a univariate function. Okay. And in particular, it's a univariate function that when you understand how the indices are correlating with the pictures, it's connecting one node here to another node here via this edge. So these activations that were on the nodes via this factorization procedure passing to the determinantal. So there's two steps: passing to the determinantal and then doing this reshaping procedure and this sparsification. It basically gives us these univariate functions that the Can theorem requires. So this is defined to be, I'm defining some phi's, phi I Q L plus 1, Z K alpha L. Okay. And of course, when you look at this, it's obvious that the way that I've written these things depends on parameters. So these are activations that if you randomly initialize your B's and A's will be a terrible approximation to your target function, but then of course we can regress on them with whatever your favorite learning algorithm is. Okay.
Jim, the
Yes.
W's that you're restricting to that have this AB factorization, they of course only can have rank n, capital N. So when you're training,
These W, yes, that's right. The W's have rank n.
so that's a very strong condition. When you train the W's, do you train with that constraint, or do you train them and then take an SVD and throw away everything other than the largest n principal value?
Good. You're saying that it is wildly inefficient.
Well, I'm just wondering how
yeah.
you get who's ranked.
So the training code that I wrote, I'm going to show you two training codes. The training code that I wrote is the one here, where I go from MLP small to the Can, and I'll show you some results from there. Just like last Thursday, my collaborator Thomas did this. I forget if he did anything special to address the fact that we have these rank n W's rather than rank Bn squared. Yeah, I'm sorry, I don't remember. One comment he did make on the code that he ran, and the results are complementary and we'll talk about them, is that these are enormous MLPs. These are enormous. So in particular, just looking at it, MLP, this is worth a different color. So MLP big has order n to the fourth parameters. MLP small has order n cubed, and Can has order n squared. Okay. So the sparsification is dropping you down pretty substantially. And this is a theoretical result, like this is just all equations. The question is like, how does it do? That's another question, right? And you might also ask, how does it do rather, presumably this is not going to be as good as some enormous MLP, right? But the point of sparsity is what is a good sparsity map? It's not to compare the small thing to the huge thing. It's to ask, are there different sparsity maps and are some of them more principled and better than others? And that's what I'm going to claim is true. Yeah.
To judge how good it is, don't you have to compare the small thing to the big thing? Is there some, again, not theorem, but claim about the relation between these things?
How big this is compared to this?
See, you told me that, and now the question is how well can the small thing approximate the big thing? That's what I would think you would have.
Theoretically or on data?
Either way.
Yeah, I'm going to show you the data in a second. Yeah. I'll show it to you right now, actually. Okay. Okay, I have 10 minutes, so I better switch to the slides. On the sparsity front, MLP big is this huge MLP. The only thing that is not vanilla compared to the norm is that I have these varying activations where they vary from sigma 1 through sigma b. And I'm zooming in on any intermediate couple of layers, taking the weights from rank bn squared to be rank n, passing to a determinantal variety. And then in the process of doing that, I further have to sparsify. These slides are rough because these are results from the last couple of weeks. Okay, so this is work with Thomas and Fabian. So this is from MLP Big. This is Thomas's plot. You're going to rightfully complain about the plots. It's because we need to rerun them. We really should zoom in on this region. So the idea here is we start with MLP Big, and you can bring to can in this discussed way. So we end up with a can coming from MLP Big. And then the question is, what's a method of comparison? So compare against uniform sparsity applied to MLP, MLP big to make it the same size as can. So instead of doing this specific sparsity map that was motivated by Kolmogorov-Arnold, you could just say, I'm going to take my weight matrices, and given the size of the can, or really any arbitrary sparsity, I'm going to zero out randomly, uniformly, some set of weights. So this is a very simple sparsity map. One would not expect this to be optimal, but it is a good place to compare. So we did this, and then we trained on MNIST. So this is the sparse MLP with the random uniform sparsity, and then it comes way down. This is the can result. So I'm plotting this. We're plotting this here. This is the can result all the way across. But the actual number of parameters is also here. So comparing the MLP, you're supposed to compare the red line here to this blue dot to this red line because they have the same number of parameters. But we're just plotting this red line across so you can see how the sparse MLP gets to this point. Now the plot is a little bit, so good. So on MNIST, 35% accuracy is not great. 82 is what the can is getting. And then this is what the sparse MLP is getting before it comes down. But the key thing to mention that is misleading about this plot is that the can has 0.04% of the weights of MLP big. So this is a very small network within the big network. And so the point of comparison, we should really do this on a log scale and zoom in. The point of comparison is this red line at 82% to what's down here at 35.
This is first training and then randomly sparsifying, or this is.
This is sparsifying ahead of time and fixing the sparsity map and training from there. Yeah. Mm-hmm. Okay.
So how do you sparsify in MLP? What's the procedure?
Yeah, so you take your weight matrices and you just randomly, so you have some fixed amount of sparsity, the probability of zeroing out a weight, and you just choose to randomly zero out those
Or you
weights.
don't zero out the smaller weights.
You could do that also. This is at initialization. So the idea that smaller weights are more informative than the others is something that often emerges during learning, that some weights are bigger than others and you might zero out there. You could zero out the smaller weights also at initialization.
You would zero out after training, right?
That's normally what you do, but here we're doing it at initialization. So we're trying to study, given a fixed sparsity map before you train, and then forcing that sparsity map, which sparsity maps are more principled to apply prior to training. That's what we're asking. Yes.
So is that sparsity map found relative to the larger MLP? How was that initialized?
This one here. So,
Yeah, so you say you started by training with a fixed sparsity map. What was that established with respect to?
but with respect to the big MLP. So we know from our CAN procedure how many parameters there are. And so then like here we would say 40% of the weights in the big MLP, we're just going to randomly zero out from uniform.
You start with the big MLP,
Yes.
and from that you construct your fixed sparsity map on which you trained your.
We apply the sparsity map to the MLP, and that's going to zero out a bunch of parameters. We're going to fix them to zero, and then we're going to train from there.
And that last dot, just to be clear, is 1 minus 0.04. That's the number of weights. It's not 1.
That's right.
Okay.
That's right. So it's like 99.6% have been zeroed out here. So it is not 1. It's this 1 minus. Yes. Thank you. Yeah.
Is it surprising that, I guess, for all the data points except the last one, that it's pretty even up until.
From my point of view, this is a bug of the plot, not a bug of the method. You're asking, should it be surprising? I think it's not surprising because here I still have I can also give you numbers. MLP big in this case has like 6 million parameters. And the can way down here has like 20,000 or something much, much, much smaller. And so it is very sparse. And so here, you know, if you're like this one is 90%. So you only have 10% of the weights left over, but 10% on 5 million is still 500,000. So that network is still much bigger than this can, which is, I mean, Thomas gave me this plot last Thursday, and I knew I was going to have to explain the caveats in the plot. But I think that's not surprising at all, because this one has far, far, far fewer weights. And yeah, I mean, an MLP with going from 5 million, order 5 million to order 500,000 parameters should still do pretty well on MNIST.
But just to throw out alternate scenario, could be just some sort of percolation transition going on. And once you got to this tiny number of MLP weights, it's just disconnected the network.
Yes. Right, because if you do the limit that you really sparsify everything, then it's a disconnected graph and it can't learn at all. Yes,
So
yeah.
that would not be a fair comparison, I would say.
Good. So I think you're saying that in applying these sparsity maps, we should make sure that we draw ones that are not inducing disconnectedness. Yeah, no, I agree. Yeah. Yes.
Just curious about general mathematical construction.
Yeah.
So if we start with MLP big,
Yeah.
for each given node of degree D, you map it in D edges.
Uh-huh.
And from there, like, could you tell me a little bit more about the nature of this map? Is it invertible? How do you recover the information loss?
Sparsity map is not invertible because it's
Yeah,
passing down to a smaller subnetwork. Yeah, I mean, the two-step process is to, so these weights are living in some space of matrices, and I'm going to pass to the determinal variety within that space of matrices that takes me from size bn squared, rank bn squared down to rank n. And then from there, there's these Kronecker deltas that came in that were crucial, because even when I go down to the bn, from the bn squared to the n, I still have dense matrices, fully connected matrices, connecting all of the edges in one layer to all of the edges in the other layer. And when I do that, I'm going to have tons of connections between the ith and jth node of the can layers, but really I only want one. I want learned activations on the edges.
okay.
So-
When you say dense, it doesn't mean topological.
No, it's not. It means full.
Okay.
Yes.
Do you understand correctly that the matrix W that corresponds to the actual can is not actually sparse itself? It's a product of two sparse matrices.
That, I mean, it is still lower rank, so in that sense, it's sparse. It's still much lower rank. It's rank order n instead of n squared, which from the size of the matrix you would have thought it was rank n squared, but it's not. It's rank n. And then indeed, it is. There's a matrix factorization, and then the next thing you do is to that matrix factorization, you apply these sparsity maps deltas.
Yeah. So my question is, have you considered applying the sparsity map to the this factorization instead of applying it to the full matrix W?
Sorry, to the
Yeah. So
sparsity map is applied to the A's and the B's that in the factorization. And it's actually kind of essential, because in doing the A-B decomposition, you're gaining this intermediate layer. And then when you compare can layer to can layer instead of MLP layer to MLP layer, it's clear that you only need 1/2 of each matrix factorization for any given can layer. So it's a little more complicated than that.
So for
Yes.
this experiment,
Yeah.
did you apply the sparsity map to matrix W or to A and B?
I applied it. This is to A and B. Yeah. Yeah, Mike.
Another interesting thing to see, instead of doing the sparsification, you could say, try to find a simple algorithm to compress the MLP big into the can. So like, it seemed like there were two choices. There was the A/B factorization and
Yes.
the rank event. And then there was this choice of putting in the delta functions and, making something rank 1.
Yes.
And you could just optimize both of those choices, and that would be some kind of can, trying to approximate the big network. And then how well does that do?
So what is it you're trying to optimize? I think I missed
No,
that.
is there a simple compression procedure which, given an MLP big, always gives you a can, and you've optimized it in some simple way. This is the best can.
Good, best can that you can get out of it. I don't know the answer to that. Presumably the best can is the largest can.
No, it's not. That's right. It's a hard question in general, but
Yes.
given a simple procedure, so I just outlined a simple procedure. Just make your choices, of A/B factorization,
Yes.
delta function projection.
Yes.
Make those two choices optimal.
In terms of there might be other related choices that you could make and then do it. Yeah, exactly.
Yeah.
Exactly.
How well does that can?
And one of those places where that where there would be choices to make is that there might be sub cans, there might be big cans that you could fit in or little cans that you could fit in into these intermediate layers. And the relative importance of that, I mean, you could optimize on that. I guess the thing I don't know is that the natural guess is that the biggest can is going to be the best can. So
My question is just kind of, is there a simple compression procedure to get a good can?
I don't think we know the answer to that yet. We know this fixed map.
I'm proposing something. Yeah, but let's just talk.
Yeah, and the choices you're proposing making are different size cans.
No, let's just talk about it.
Sure. Good. I do have a whole nother part of my talk, but maybe I'll finish this part first. I'll be very fast on the third part of the talk because it's easy. This is sparsity from MLP big. This is sparsity from MLP small. Here again we have a plot I tried to put colors on last night, but it was yelling at me that the pickle file has CUDA-based stuff happening that can't work on my laptop. So the ones that say false, the different choices on this axis are different choices of these activations, GALU, sigmoid, TANCH, et cetera, sigma 1 through sigma B. And the ones that are false have random uniform sparsity set to false. So those are the cans, and the ones that say true are the random uniform sparsity applied to MLP small. And then we again trained on MNIST. Sort of what you see systematically is that the left-hand side in any given activation is always higher. These are all the cans, the higher peaks. And these are the random uniform sparsities of MLP small. Now, if you're looking at the numbers, you'll notice that Thomas's experiments and my experiments are a little different. The cans are sort of all in the low 80s, which is consistent with what he's seeing here. But his random uniform sparsity is way down here at 35. And all of my random uniform sparsities are, higher than that systematically. And so the difference here is that he is sparsifying the entire weight matrix of the entire MLP big, whereas what I'm doing is passing down to MLP small on the determinantal and then sparsifying from there. So they're different random uniform sparsity maps. And so what these experiments are telling you is that yes, cans are doing, can sparsification seems to be more principled than these other ones. But also, if you even just ask, is there value in going to the determinantal before you sparsify, the answer is yes. So if you just randomly, and maybe this is related to the percolation question Mike was asking, if you just randomly sparsify a huge MLP with random weights, versus passing to the determinantal first and then sparsifying those smaller matrix weights, but still with the same number of fixed parameters, passing to the determinantal first before sparsification actually seems to be better. This is an observation. We don't really have an explanation of that fact yet, but we're happy that we're sort of seeing things start to emerge. We're really interested in sparsity. What are principled sparsity techniques? And these different random uniform sparsity implementations give different results because they're mathematically different. That's all I have to say about this part of the talk. And then I'll lightning through the
kind of just said you don't have an explanation, but do you have any speculation of hypotheses why it might lead to something better? Like if you're using the factorization, maybe you're retaining some structure that's like helping you even if you're sparsifying. Like, do you have kind of some speculative comments about this?
Yeah, I mean, I have worried about things like if you totally sparsify, things sort of start to become very disconnected. And so applying the sparsity to the determinantal as opposed to the entire matrix space, there's probably some sort of observable about connectedness that you could measure in the associated graph that I'm worried about sparsity inducing pathologies that will hurt learning. And so to identify those, whether it be disconnectedness or something else, it might be that the probability of obtaining one of those pathologies is different under these different maps. But as you said, this is speculation. Sure. Yeah.
Could you speak a little bit more on the hyperparameters that were set for MLP and maybe like how the trading stability was as you were, trading these
Yeah, the random uniform sparsity training was very unstable. The CAN was rather stable. The hyperparameters, I mean, this is based on the size of MNIST, which when you flatten into a vector is like 789 or something. I don't know, some order 700. Of course, there's 10 outputs in MNIST. There's a 10-dimensional output. And good. From there, we sort of chose sort of minimal width that was relevant for the problem. The key thing is that you have to be able to do this factorization. So that sort of sets the minimal width. Yeah, Mike.
Did you say anything about the choice of the sigmas?
No, right. And so that was one of the things. So when, of course, when I coded this up for the first time, I had this idea. It's clear what the map is. I just like chose a few. I chose like Rayleigh sigmoid tant or something. I don't know. I just made something up. And it sort of worked. And that's why my collaborators were bothering me like, what? Well, I just chose it. So we tried a bunch of different possibilities. You'll notice that it is a little bit sensitive to the choice of the different activations. In principle, the right thing to do is to choose activations that are known to be good for 1D approximation theory, because in the can, that's what they're doing. So in particular, we did B-splines in our original paper, and I'd love to put those in. But right now, it's just purely experimental, putting in natural things that we put in. I'll take more questions on this at the end. I want like 1 minute on the third part of the talk, because it's very easy. This is symbolic regression. This is data. If I ask you what is the equation for that data, you have to work hard. If I plot that data and I ask you what is the equation for that data, it's a bit easier. There's some sort of sinusoidal looking thing, but it isn't continuing to fluctuate. So it's some sort of damped sinusoid. And this is a Gaussian damped sine, okay? So you might have a speculation for an equation for this, but if I just hand you that without a lot of work, you're not, no. The question is, can large language models do this? And so we came up with something called visual symbolic regression, where we prompt an LLM to guess a functional form based on raw data or images of raw data versus images of data. So in this case over here, it was given just the raw data and it suggested a functional form. The image is here just to show you what the data looks like, but it was not given that. It suggested a functional form, which we then optimized using SciPy, and it came up with this, okay? But when we gave it the image, rather than the raw data, it guessed the functional form that was better, and when we optimize it with SciPy, we get the red curve. So in the same way that humans might want to see data in one form versus another, this is like the second geometry part, because there's literal, images of geometric things. We're hoping that giving an image rather than data to a large language model is going to help. So there's a long story that I said I'd only take a minute. We have something called LIMLEX, which is 1D visual symbolic regression together with genetic algorithms, and it does pretty well. And here's some more evidence that it does pretty well. But 1D symbolic regression is not necessarily what you want. 1D symbolic regression, of course, we want higher D symbolic regression, but you can go beyond 1D with Kolmogorov-Arnold. And so a basic fact of our Kolmogorov-Arnold representation, you can see here, is that we literally have images in our old package that we could then apply this 1D symbolic regression to and try to use the visual part of large language models to do this 1D visual symbolic regression with genetic algorithms together with CAN to bootstrap to higher dimensions. And so that's what we did. That's the symbols third part of the talk. I didn't take 1 minute, but I took 3, so thanks.
I think we should just